Okay, good morning, everybody. Sorry for the delay. I was trying to figure out how this works. The title of this talk is a bit threatening, suggests a lot of math. The answer is yes, there's a lot of math. But the good news for you is that Dr. Horst asked me to expose everything without math, which resulted in a very useful exercise, and I try to do my best to illustrate the concept without the use of deep mathematics. This is all based on a recent work with people from Alan Turing Institute, KAUST in Jeddah, and local collaboration at Khalifa University with a famous genetist, Saleh Ibrahim. This is the roadmap to this talk. I will face the problem of data science from the perspective of what I term 3Ds complexities, by meaning data structure, data cardinality, and data domain. And I will provide an overview showing that for each of these aspect, networks are everywhere. And I will illustrate the last finding concerning temporally evolving networks. Some tips about my trajectory. I've been working in several places. You might wonder how old I am, since I've been in so many places. And since 3 years, I'm in Abu Dhabi, and I've now joined. I'm proud joiner of ADIA Lab. And I've been working in several research centers associated with applications to computational genetics, seismology, climate change, tsunami, and recently I've been more involved with health data science and genetics application. Regarding my research interests, I move within the edges of machine learning, computational statistics, and spatial statistics, with a universe of applications to genomics, environment, climate, genetics, and so on. I enjoy very much the talk by Professor Miguel Hernan and his sectional view of data science according to the free task. I will provide a different view, and I will start by mentioning that the business of data science has been going over and over for about 30 years now, with several contributions coming from, in particular, from statisticians and computer scientists. You can see Leo Preiman, Peter Huber, David Donoho, who wrote a very influential paper about 30 years ago. And the common view of data science is a proper intersection, a proper blending of machine learning, computer science, and statistics. This was not a smooth convergence. There was a lot of debate. I remember an article by Andrew Gellman where he was claiming, why do we need data science if we had statistics for centuries? And then I saw another article by another scientist saying, hey, we have data science, we don't need statistics anymore. So certainly there has been a lot of intellectual activity around the way we should conceive data science. But since I would start by saying that since this is a science, it should have some intellectual content, organization, and reliance on test. And the way it developed is, as was mentioned by Miguel, accelerated development in computer devices, formal theory of statistics, and increasing availability of data. There is also the counter view of data science, which is way more practical, and it is oriented to how to handle with what we term data life cycle. So how to capture data, how to process, analyze, maintain, and communicate. So there's no uniform view of data science. Depends on your perspective. Depends on from where you want to challenge or where you want to work with. This implies that within the business of data science, you will have data analysts, data engineers, data business analytics people, and to be very honest, when all this happened, I was not too happy because I was questioning myself what will be the role of statistics and math within the business. And actually, there is plenty of stuff to do. Math has never been better than now than within the business of data science. So I will provide this view, which is complementary to what Miguel was mentioning before. From the perspective of a statistician, I would see data science as challenging what I term 3D's complexities. So I will refer to data structure, data domain, and data cardinality. I will explain each of them with some example, and then I will show you how networks are everywhere in each of these directions. Regarding data structures, Miguel was mentioning before that the problem of big data, massive data is everywhere. Actually, statisticians have been dealing with huge data sets forever. 2 centuries ago, we already dealt with census data. What makes data science more complicated, one of the things that make data science more complicated is data structure. We don't deal with tables anymore, or at least we don't live exclusively with tables anymore. Data can be objects, can be functions, can be networks, can be everything. This justifies the development of statistics of objects, of massive literature on functional statistics, functional data analysis, and so on. I had to deal recently with the networks in terms of data structure, not in terms of data domain, with the genetic migration in the Arabian Peninsula, which is apparently an unsolved mystery. While genetic migration has been well understood in many other sides of the planet, apparently there are many sources of complication in order to explain genetic migration in the Arabian Peninsula. There are 2 main theories. One is related to northern route from Sinai and Egypt, and the other is related to East Africa. Recently, we challenged the problem from the perspective of Yemen population, and we had a massive data set, 46 genomes, 169 genotype arrays from Yemen, and more than double, no, around double of genotype arrays from other side of the planet. This is a picturesque representation of the situation where we disentangle the genetic pattern according to different locations. And one can have a look at clustering of similar patterns and similar characteristics. Actually, if you have a look at this picture, you won't understand much. But it turns out that this is a starting point to build up a circular hierarchical networks to justify the relationship within different genotypes. And you can end up with this stuff, where starting from each of the genomic variety, you can build a hierarchical network that will allow to build in turn clusters and associations within different countries. The story is that this representation, you can find any fancy representation in the literature. These representations don't take into account the topology of the network, which in turn allows to understand what is the practical distance between variables on a network, which is not well understood in the current network literature. Other examples that I have recently seen in genetics come from metabolites and RNA for mice with mitochondrial mutation. And you can see this is the common way to visualize these networks where you have a classification by color and classification by size of the dots, which illustrate the intensity for each of these variables. Or sometimes you can find these kind of associations where you can see edges connecting the vertices of your network, where some of the vertices can have loop, some of the edges can be nonlinear, some of the edges can overlap. The message is that linear networks which have been massively used in the last 30, 40 years are not suitable to describe this kind of relationship. What about this network? Here, I should mention that the linear network is just a merging of segments on the plane where the edges are not intersecting between each other. And here we have plenty of intersection. So how to describe mathematically this relation through a proper mathematical model. Regarding data cardinality, which was the second aspect, I termed this the big N and big P. N is the number of observation for each variable, and P is the number of variables. So I totally agree with Professor Miguel that massive data sets are everywhere. And of course, we have computational challenges. The first computational challenges I can remember from spatial statistics were related to estimation through maximum likelihood and prediction through best linear unbiased predictors. And apparently, we found ourselves in the position not to be able to do no estimation, no prediction, because the computational cost was of the order of n to the cube, where n is the number of observation. So, in my opinion, the challenge here is to find suitable method that allowed for a reasonable compromise between statistical accuracy and computational scalability. And there have been plenty of proposals to milden the computational burden induced by classical statistical methods. And finally, I go into data domain. I remember when I started my PhD, every instructor in stochastic processes would mention time series. And then at the end of my PhD, people were talking about spatial statistics. And during my postdoc, people were talking about space-time statistics. So from one dimension, we started challenging space and then evolution of spatial phenomena over time. And the rationale was from a limited number of observation, you reconstruct the picture, and then from a limited number of observation, you will reconstruct the movie. And data domain became more and more complex. You can see on the upper side of this slide a stream river flow with a given direction connecting river baselines, or observations from a satellite where you need to take into account the curvature of the planet and the fact that observations are not on the surface of the Earth. How to build mathematical models for that. Or brain connectivity, where you typically have a network, a very complicated network where realizations are not only at the vertices, but also at the edges. So you have to be a little bit more creative because your process is continuously defined over a network, something that we would have never imagined before. I don't know if you can see this. These are two other examples I've been working with recently. On the left-hand side, you have a clear water river basin data, where you observe temperature, pressure, and other variables for each of the dots. And the dots are connected by the stream river flow. Would you be able to describe this through a linear network? The second picture is about traffic accident. This is a pixelization of the main road in Salt Lake City. And what you want to do is to build up a point process model to illustrate the intensity, which in turns will tell me intuitively the probability that an accident occurs in every part of this street. Again, the literature and the state of the art is limited with respect to this situation. So more work is needed to build up generalized networks, which allow to map continuously a process over edges or vertices, which allows to nonlinear edges. And of course, there are many challenges related to this. You can think about a topology of the network, how to describe this topology. And then once, if you're lucky and you're able to describe this topology, how to measure distances over these fancy networks, which is something absolutely non-trivial. And what are the impacts of this new machinery on machine learning, for instance? How to do supervised learning and unsupervised learning under this new framework. And the implications are massive. On the top of this slide, you have a linear network, which is just a merging of segments on the plane, where the segment can intersect at most once. And this is a picturesque representation of a generalized networks, where you can have edges which are not straight lines. They can have a curvature, and they can intersect. So basically, think about road networks, where you will have the dots representing red lights, and the intersection between the edges might be tunnels. So how to build this network is the first challenge, how to assign a proper topology, and then how to construct metrics over the network. You cannot perform any machine learning technique without building a proper metric space to represent this network. Which network would you choose to represent this situation? Here you have a river with a stream flow with a proper direction, representing connections between temperature. Which one would you choose? Well, the answer is the one on the right-hand side, where you can depict a graph with a given flow. The problem is that for this graph, building a given process is definitely non-trivial. And I will show you why later. Here we have other examples of networks which cannot be represented through linear ones. For instance, bulk crimes in Chicago. And on the right-hand side, the walks of spiders along bricks, which follow very strange, very weird path. And you can see on the left-hand side that for the same network, you can imagine different metrics. And you can have the Euclidean distance, which will be just a straight line connecting the dots, or a network distance, which will try to approximate the network as best as we can, or the flow distance whenever we have to take direction. All these choices are related to different mathematical settings. And if you want to solve this, you need to do math. And specifically, the math that you need is old-fashioned. So the three guys that you see in the picture, well, on the bottom you have Euler, the father of graph theory. On the left-hand side, Gelfand, from which the terminology Gelfand pairs. And on the right-hand side, you have Iso-Schoenberg. So these are apparently very far disciplines in mathematics. One is related to graph theory, which is a smart way to challenge a network. The second is related to approximation theory and harmonic analysis on very abstract spaces. And the third is related to transforming a given geographical space into some abstract space. Why do we do that? Because when we move to abstract spaces, we find nice solution, and then once we find a nice solution, we go back to the geographic space to provide you an answer. And this is what we do. So basically, we transform this network into some suitable abstract space that we call an Hilbert space. Over this Hilbert space, we measure distance linearly. And once we are able to compute the distances, then we can go back to the network and implement all the machine learning machinery. How much time do I have? Okay, thank you. And And the way to measure the distance, once you do this operation to embed a given network onto some suitable Hilbert space, the way to measure distance becomes almost immediate, because if you want to go from the point V0 to the point V2, you will just have to compute the length of these curves from V0 to V1, and then the length of the curve from V1 to V2, and then you will just need to sum up these two lengths. So at the end, by making things difficult, we make things easier. Because by providing this abstract representation, then we are able to provide easy solution to the practitioner. So to summarize this part of the findings, we have been able to provide suitable topological structures for general networks, which allow to challenge a wealth of practical examples where linear networks are not suitable. And we have found a smart way to compute distances over abstract spaces. The implication for machine learning is that we can build kernels. So one can implement all the machinery reproducing kernel Hilbert space methods over these spaces. And we can do any supervised or unsupervised learning techniques, something that was not feasible before. There are situations, just to be very picky, where these methods are not properly working. There are limitations according to the metric you use. For instance, you cannot merge to cyclic graphs or to rectangular graphs because you have some topological problem. There are still some things to be solved, but we are on a good way to provide a final solution. Time-evolving networks. You can find applications everywhere, from brain connectivity to local brain connectivity with age, to synapses formation and connectivity through the years, and so on. What you can see from these pictures is that the network is evolving over time. So you have a different number of vertices from one instant to the other, from one time instant to the other, and you have a different number of edges and connections. So how to build a mathematical model for this is definitely non-trivial. You can see this in traffic roads. It happens all the time in Abu Dhabi. Sometimes I see a red light, and the day after there is no red light. There always works, and cities evolving very fast. How to build a temporal networks? We have two alternatives. One alternative is to suppose that the topology of the graph is temporally invariant. So you just repeat the graph over time, over and over, and then you can build a proper space-time model by using this advantage. And this is definitely simple, but it doesn't answer my question that we illustrated before. What happens when the number of vertices is changing over time and the edges are changing over time? So I will skip this part of the application because there is no time. So the alternative is to use adaptive topologies. What does it mean? Well, the concept is a bit intricate from mathematical viewpoint, but it can be illustrated in the following way. This is my network at time 0, and then this is network at time 1, and the network at time 2. So you can see things changed. I have a new vertex upline showing up from A to B, and different connection from B to C. Okay? One solution is to complete this network by summing up these temporal slices. but the problem is that you lose connectivity between the vertices. So if you want to go, for instance, from point E at time 0 to point D, you cannot cross diagonally the network, because you would lose all the nice mathematical properties. And the problem is that the sum of temporal networks is not a space-time network. This is a big problem whenever implementing the machinery, the design machinery in terms of machine learning models. So this model is inconsistent because distances, whenever you add slices, shrink and become unrealistic. So we proved that the only way to build a consistent space-time structure for this network is to make time circular. So basically, that means that when you go from 0 to 3, at time 3 you will come back to 0. You might say, how come? Time is linear. Well, not necessarily. You can think of plenty of situations where time might be thought of as a periodic variable. Just think about ozone concentrations during the day, and you will see that there is a periodic behavior. In many environmental phenomena, time is periodic. But in order to build a suitable mathematical structure, we need to resort to this circular representation. And I'm not aware of any other construction that might allow to keep consistency in the construction of these space-time networks. Impact of this research, well, impact will be in many aspects of more applied sciences, for instance, functional data analysis, geostatistical functional processes, and statistical visual animation. And of course, in machine learning, this will have a lot of development in many supervised and unsupervised learning methods. So I'm finished, and then thank you for your attention.